So in the last class we discussed about the compression member design as per the limit state method and some codal provisions and assumptions as per IS456 2000. Okay, so we calculated the maximum load carrying capacity of the column in the last video. Okay, so here we are going to take some design example of your column. Okay, so let us take the example. This is for the example for design of your axially loaded column. Okay, with minimum eccentricity. Okay, so it is not true for the design of your column with axial load and uniaxial bending. Okay, so we are taking the example for axial load only. So let us take a section here. So we have a section, let us take it as 250 of 300 section we are taking. So let us take 4 bars of 12 mm dia with steel, that is torch steel we are using here. So width is 250, depth is 300 mm. So we can calculate the value of your that is AC, that is area of this compression, that is compression is due to concrete. So area of concrete, it is equal to 250 into 300, that is 75,000 mm square. Then we can calculate the area of steel as number of bars that we are using, 4 12. So 4 number of 12 bars of 12 mm dia, we can calculate the value of steel as 452.38 mm square. Here it is coming. So now percentage of steel, it will come out to be, that is area of steel divided by area of the cross section, that is this whole cross section. So 75,000 multiplied by 100, so we are getting the value here 0.603%. okay, so this is the amount of the steel that we are going to provide in this section. Now this amount of steel is less than 0.8%. okay, so the code says that we need to provide minimum of the steel which is equal to 0.8% in the column. okay, so that's why we cannot provide this value of steel here. okay, so let us take some codal requirement for longitudinal steel that is given in your clause number 26.5.3.2 at page number 48. Please check it, of IS456 2000. So the minimum dia that we should use in the column, it is taken to be 12 mm. So if we want to use, if we are using the bars here, then the minimum dia of these bars should be equal to your 12 mm, not less than 12 mm. This is recommended by code. okay, and second one is at least 4 bars in rectangular column. If you are using a rectangular column, then minimum number of bars that you are going to use is 4. okay, not less than 4. And for your circular column, we need to use 6 number of bars. okay, this is given in this clause, you can see that. okay, so this is these why we are studying this, because we need to follow these recommendations while designing the column section. So that's why we need to have a check on these values. okay, so here you can see we are providing 4 bars of 12 mm dia. We can't provide 4 bars of 10 mm dia. okay, because the code says the minimum dia should be 12 mm. clear? Now the percentage of the steel, that is longitudinal steel, it should not be less than 8%. okay, the percentage of steel that we are providing, it should not be less than 0.8%, and it should not be greater than 6% of cross sectional area of the section. So we need to calculate the percentage of steel within this limit, which is provided by the your code, IS code. okay, so here in the numerical problem, we are getting the value as 0.603%, which is less than 0.8%. So in this numerical problem, however, we have calculated this area of the steel for the load which is coming on the column. Okay, so this section is going to take the load properly. Okay, so there will be no any problem if we will use this amount of steel, this percentage of steel. It is going to take the loads, but our code says that if the value of the steel comes less than this, then we should not use the value which is coming out to be less than 0.8%. Okay, so that's why what we can say that it is not just about calculating this areas. We need to calculate all the things under codal provisions. Okay, so that's why we need to follow this strictly. So we are not going to take the percentage of steel up to 0.603% here. Okay, now next, moving forward. Now next is your normally the higher percentage of the steel is taken up to 4. Okay, it should not exceed 4%. Now minimum cover to the steel, it is up to 40 mm, not less than this. Now spacing of the longitudinal bars. Now the spacing that we are going to give in the longitudinal bar, measured along the periphery of the column. It is measured along the periphery. Okay, the spacing that we are going to give, it is measured along the periphery of the column. So it should not be more than 300 mm. Okay, it should not be more than your 300 mm. 300 mm is the distance, is the spacing. Okay, it is the maximum spacing that is allowed. Now in case of pedestal, nominal longitudinal reinforcement not less than 0.15% of the cross sectional area shall be provided. Okay, so in case of pedestal, we need to calculate the longitudinal reinforcement up to 0.15% of the cross sectional area. So these are the codal requirements you can see in code that I mentioned. Now here the percentage of steel is coming out to be 0.603%. okay, now which is less than 0.8%. so now let us find the value here, the load value. Okay, so the load value which is coming out here is 0.4 FCK AC plus 0.67 FIS. We'll use the formula. Now we'll put the value as taking FCK as 20 and Fy as 415 Newton mm square. We can calculate the value of Pu. We'll put the value here and we can get the value of Pu as 725 kilonewton. Okay, so now here the load which is coming, it is coming out to be 725 kilonewton. So for this section, if we provide the cross section of your this, that is it was provided as 250 into 300. okay, it is going to take your load of 725 kilonewton. Okay, now this section, maybe this section can take load less than 725 kilonewton. Okay, so we can reduce the section 250 into 300 to 250 into 250 also. Okay, then we can find the value of Pu. Okay, so here what we are trying to say that the load which we have calculated for the section to be 250 into 300, okay, that is coming out to be 725 kilonewton. So there might be chances that the load taken up by this section can be less also. Okay, so we are reducing the section here. So this is all about designing. Okay, how perfectly you can design. Now if we'll take the design to 250 into 250, okay, so then we can calculate AC in the same way and AS in the same way. We will put the value here Pu. Okay, and we can calculate the value of Pu as 625.678 kilonewton. So here the percentage of steel is coming out to be 0.723%. Okay, so here even in this case your percentage of steel is coming up less than 0.8%, while we have reduced the cross section. Okay, so now generally we need to follow the code design practice and provide minimum steel for design, taking into account your shrinkage, creep, etc. Okay, so if we'll design for the section, if we are designing any column section, then it should be under your codal provisions, and the minimum steel should be about 0.8%. Why to do this? Because if in there if in case there exists any dispute after you have designed the column section, okay, so then and if you have taken the design considerations under codal requirements, then nobody can ask you why you have done this. Okay, so this is all about your perfection. Okay, so in this above question, so we provide 6 bars of 12 dia. Okay, so then percentage of steel is coming out to be 1%. so now your codal provision, that is 0.8%, we have achieved that. Okay, now the minimum steel is 0.8%. okay, so when we were using 4 bars of 12 dia, it is coming out to be 0.7232%, which is less than 0.8%. okay, so we need to modify this value. So now we are using 6 bars of 12 dia, so then the percentage is coming out to be 1%. okay, so at least we need to provide 6 bars in 250 by 250 section. So we need to provide 6 bars here in this section, okay, instead of using the 4 bars. Okay, so this is the thing which is important. Now we can talk if we talk about the lateral ties. So there is also provision for lateral ties in your code IS456 2000. So the pitch of the lateral ties, that is minimum of the least value among the three. Pitch means if you are providing this column and this is the longitudinal male reinforcement, then these are the lateral ties or transverse reinforcement. So the pitch is this. Okay, so the pitch of this lateral ties, it should be least of the three values. What are the three values? Least lateral dimension of the compression member, okay, and also 16 times the smallest diameter of the bar longitudinal reinforcement. Suppose you are using 2 bars, one is a 12 dia and the other one is your 14 dia. So we are going to take here the smallest diameter of the bar. Okay, so 16 times the smallest diameter of the longitudinal reinforcement and 300 So we need to take the least value from all these things, three values. Okay, so minimum of the value, that will be the pitch of the ties. Also the diameter of the lateral ties, it should not be less than 1/4 the diameter of the largest longitudinal bar. So here we took the smallest diameter, so here we are taking the largest longitudinal diameter of the largest longitudinal bar. So the diameter of the lateral tie should not be less than 1/4 the diameter of the longest longitudinal bar. Okay, so here so as per these provisions, we are going to design the section. So let us take another example here. Let us take the load to be 1200 kilonewton. We are using M20 and Fe415 steel. So the load value will be calculated like this. We are going to use the formula PU equal to 0.4 FCK AC, 0.67 FYES. So now here in this numerical problem, we are not provided with the steel, how much amount of steel we are providing in the section. Okay, and we are not also provided with the dimensions of the column. So we need to assume the steel here. Okay, so we'll assume the steel within limit, that is 0.82 0.8% to 6% within that. Okay, so let us take most of the time we take the steel to be 1%. Okay, so let the area of the steel which is coming out to be here will be 1% of the total area of the section, so 0.01 of AC. So we can calculate, we can put the value of this AS now here in this equation. Okay, so when we'll put the value here, so we can get now the value of your AC from this we'll put here. Okay, so PU we have calculated, you can check the calculation here. Okay, so AC when we'll calculate, it is coming out to be 11312.09 mm square. This is the amount of the concrete area of the concrete, okay, section. So this is the overall section that we are getting. So now provide a square column. Okay, so we can take the dimension if we calculate from here. So let us take we are providing a square column of d by d. Okay, so we can calculate d from this. Okay, so d square will be equal to AC. So we can calculate d from here, it is coming out to be 333.63 mm. Okay, so let us provide here the area of the provide 350 into 350 column. Okay, so when we will provide this 350 into 350 column, then area of concrete is coming out to be 122500 2500 mm square. This is the area of the concrete, and now area of the steel is coming out to be 1225 mm square. Okay, so now we use if we use 12 dia bar, then number of bar will come out to be 10.89, and if we use 16 dia bar, then number will come out to be 6.09. okay, so here we cannot provide 11 bars, so we need to provide 12 bars. Okay, so and also here we can't provide 6 bars if we use 16 mm dia bar, so we need to provide here number of bars to be 8 bars. Okay, so let us provide 8 bars of 16 mm dia here for the dimension 350 into 350. So area of steel will come out to be for the area we can calculate area of the steel 1608 mm square. We can calculate it, number of bars multiply by area of the single bar, then percentage of steel we can calculate area of the steel divided by area of the cross section, and here it is coming out to be 1.31%. okay, so it is more than 0.8%. now lateral ties, it should be the diameter of the lateral tie should not be less than 1/4 of the your dia of the bar that you are using. So it is coming out to 4 mm, so there is no such bars of 4 mm, so we can use here 6 mm dia bar, and no torch steel of 6 mm come in the market, so we will use 6 mm dia of mild steel here. Okay, so spacing we can calculate, it should not be more than minimum of the 3, that is least dimension of the column. Here we have 350 mm, and 16 times the dia of the bar, 16 into 16 to 56 mm, and 300 mm. okay, so we can take the value the minimum value of the 3, so it should not be more than the minimum of 3. So minimum of 3 here is 256, so the spacing should not be more than 256 mm. So here we are providing 250 center to center, so we are providing 6 mm dia bar at 250 center to center here. Okay, so here we have designed the column. So now finally we got the cross section here like this. Okay, so this is 350 we have calculated this, and the number of bars we calculated for this 350 by 350 column, it come out to be 8, so we will provide 8 bars. Okay, then the main longitudinal bars, so main reinforcement 8 bars of 16 mm dia we are taking. Okay, so 1 2 3 4 5 6 7 8. okay, so this is the your main reinforcement. Now the tie bars, we have calculated the tie bars to be 6 mm dia bar at the rate 250 center to center. So we will calculate so the tie bars we will use here and here. So here you can see we need to provide the tie bars here, okay, around these all 8 bars, and also we need to provide the tie here in between, okay, for complete resistance to buckling. Okay, so we need to provide like this. So you can provide the bars simultaneously at this point, okay. So where you are providing this, along with that you can provide this. So to reduce the complexity here, so what you can do, you can provide first tie the outer tie member here, and for the another 4 bars you can provide the bar here, okay. So but you need to maintain the distance, that is 250 mm center to center, okay. So otherwise you can provide here also, it is there is no any problem for that, okay. So here we finally designed your axially loaded column, okay. So now in the next class we'll take your column, axially loaded column, along with your uniaxial bending. So thank you so much.